Okay, some good news. So for those of you who just really love applying equations, that's the first half of today's lecture. This is going to be integration by table lookup. So when my dad was studying sort of calculus back in the old country, in the Czech Republic, in like the 60s, they really didn't have computers at that point. And so one of the ways that they would integrate is like my dad has books, full books, and the whole book is just integrals. This integral integrates to this one integrates to this. So what they would do is give it a new integral, they would try to get it to look like one of the integrals from the book. And then once you get it to look like one of the integrals in the book, right, then you can go ahead and solve it. So one of the skills that we expect you to be able to do is if I tell you what an integral of something is, you need to be able to use that identity or rule to solve a new integral. So here's a rule. Don't memorize these. There are literal thousands of these rules, right? So the skill that you'll be required is, given the rule, use it. And so there's a test question like this, where I say, given this rule, use it to resolve this integral. So here's one rule. 1 over a squared minus x squared to the half dx is equal to arc sine x over a plus c. We're going to prove this next week, but for now let's just use it as a rule. So can we use this to do this integral? Does this look close to that? Kind of, yeah? So what do we need on the bottom that we don't have? Difference of squares. And so how can we make this a difference of squares? Who remembers high school? Who remembers a technique called completing the square? You don't remember that? Okay, so we can force this to be a difference of squares. Yeah? So let's see. You are expected to know the math that you've been taught up to this point. Period. Right? Like everyone wants to keep forgetting trig, but we keep coming back to it. Okay, so let's just look at 8x minus x squared, right? I want this to be a square. I think this is going to be, so there's an 8. Its half is 4. So this is going to get me close, right? Or you're going to get an x squared here. Oh, minus x squared. And then you're going to get a minus 8x plus 8x. So if I expand this, you're going to get a minus, what was this? 16 minus 8x plus x squared. So I'm a little bit off, right? If this is minus 16 plus 8x minus x squared, what am I off by?
16.
Yeah, so I have to add 16, right? So I should have to add 16 to this. Everyone remember this technique? Well, I got to practice a bit.
Can we write it in like the format where it's like A, B, C type of way? So it's like B over 2, I don't know. It's like in the variable formula.
The general formula.
Well, we don't use the quadratic equation to get this. This is just...
No, not the quadratic formula, but just like the general formula for completing the square with variables.
I don't remember. You can look it up, right? We can develop it, but do I have time? If I have time after class, I'll develop the equation for completing the square. I just genuinely don't remember it. But the strategy is like you usually, when you square something, that's like the double of the product of the middle. Right? So it's usually half of that. Like usually how I remember it is I just take half of that and then I just multiply everything out and figure out what's left over. It's one of the techniques. Anyways, I'm going to erase this because you don't really need it. Okay, so that means this is equal to what? 1 over 16. Let me just write that as 4 squared. 4 squared minus 4 minus x squared to the half dx. Now what can I do? I'm not quite in that form yet. Well, what other techniques of integration do we know?
We can take out a constant.
Well, this almost looks like this. Almost. Well, rattle off any of the integration techniques you've been using. Substitution. It's literally the only one you have at the moment. So what substitution can we use to get this to look more like that?
Like u equal 4 minus x?
Yeah, u equal 4 minus x. So if we let u equal 4 minus x, this means that du is minus dx. All right, so maybe I'll just put that over here. Okay, so that means I could rewrite this guy as the integral of 1 minus 4 squared minus u squared a half minus du. Now what? Does that look like this? Okay, so finish it for me. Okay, I'm just asking you to utilize a formula at this point. So, okay, it's arc sine, well, minus arc sine. What?
U over 4.
U
Over 4.
over 4 plus c. And then we have to unroll the substitution. So we're going to get 4 minus x over 4 plus c. We'll do another one after this. Right, but again, the critical skill set required here is that given a rule, you have to be able to use it. So what you have to do is use a substitution or some clever arithmetic to try to get the integral we gave you to look like the rule that we gave you. So suffice it to say, if I give you a rule and say, use this rule to integrate the following, it's going to be possible. I'm trying to send you a signal saying, can you please rejigger this equation to look like the rule that I gave you? So we'll try another one. So usually a substitution is quite helpful here. I'll give you 2 rules this time. The integral of secant squared x dx is tan x plus c. Here's another one. The integral of secant x tan x dx is secant x plus c. So given those rules, can you try and do integral 0 to pi quarter 1 over 1 minus sine x dx.
Does that mean we have to evaluate it at the end? This will give us
Yeah, you can evaluate it at the end. Or, I don't know, maybe, I don't really care that much at the moment about the definite integration. If you can do the indefinite, like, the hardest part of doing a definite integral is doing the indefinite integral. Right? I trust that you should be able to take the difference of those evaluations.
do we have to use both?
Well, yeah, it's a strong hint, don't you think, when I say here are 2 rules? But like, really, like there are thousands of these. Right? I wish I could have brought you one of these books. If you look at the back of any calculus textbook, you're just going to see a list of like at least a couple hundred of these identities. So how would you go about doing this? Okay, I'll give you one hint, strong hint, and I'll make one lap. Okay? That's handy. Right, because what do you get on the bottom now? Huh? What do you get on the bottom? A minus b times a plus b. 1 plus sine x minus sine x minus sine x squared. Right? 1 minus sine squared x, and the top is going to give you 1 plus sine x dx. Now what?
That's a cos squared.
This thing on the bottom is a what?
Cos squared.
Cos squared, all right.
1 over cos x.
Yeah,
times sine
great.
cos
That's
x.
perfect. Okay? This tricks a lot of people a lot of the time. Right? When you have one thing on the bottom and a bunch of stuff on the top, it's usually better to break it up into individual pieces and integrate along each individual summand. Right? So the best I can ever do is give you a bunch of heuristics for taking integrals. So when you see something like this, when you see a bunch of stuff in the numerator and one thing in the denominator, one thing that you should try is to do this clearing. It may work sometimes, and it may not work other times. Okay, so now what?
Well, that's secant squared.
Right. So what do we got? We actually got integral secant squared x plus what? What's that?
We can split it apart and 1 of them will equal 10.
Well, isn't it secant tan x? One of the sine over coses become tan. The remaining 1 over cos becomes secant x. So now what? Yeah, now we can use the rules. So what is, by the rule, what is the integral of secant? Tan x. What is the integral of secant tan x? Secant x. Okay, so if I give you a rule, it is up to you to try to reformulate the problem to look like the rule so that you can use it. Right? I can't just give you this and say apply this rule. That's too easy. Any questions? Okay, so that's actually the first half of the lecture because there's just so much I can say about evaluating formula.
So this is just express this, there's no right way of doing it.
There's no right way of doing it. The right way of doing an integral is any way which gets you to the correct answer. Right? There's going to be tons of different ways of doing the same integral. All right. So please practice. I'm going to give you, there's a ton of practice in the tutorial this week. And I gave you a worksheet today, but I'll give you a ton more of exercises at the end of this. Can I erase this? Yep. So while you're doing your homework, you should be naturally memorizing useful identities. It's like the phone number principle. I don't want you to memorize rules, but if you do enough practice, you'll realize a lot of stuff comes up, and you'll naturally be able to remember it. Oh, don't forget to look at the formula sheet, by the way, for the next midterm, because we also gave you all of the formulas for like surface area, arc length. We don't expect you to remember those. We just want you to use them. All right. Okay, so I'm going to teach you a technique today, which is going to be either, well, your best friend, but also your worst enemy because we're going to be tested on it. But this integration by parts is extremely important. And here's how we motivate this. So you know that, can we expand this? Or distribute this? Is there another way to write this?
Factor one of them.
Well, the integral of the sum is the sum of the integrals. This is a nice property. Right? What we don't have is this. What is the integral of the product of two things?
We don't have that rule.
We do have that rule, actually. But it is not this generally. Okay? This would have been lovely, but it's not true. Good exercise. Show this is not, like, find me an example to prove that these two things can't be equal. It's a good exercise.
True or false?
Huh?
Is this true?
If this is on the true and false, you're going to get it wrong?
No, I was asking for you to get it.
They may be there, actually. And I guarantee some people will get it wrong. I tried to make the true-false questions easier this time around, as well as the fill-in-the-blank. So you'll have to spend, if you find yourself spending a lot of time solving a fill-in-the-blank, you're doing it wrong, right? You got to tell yourself at the beginning, the answer to this should be something easy, right? Because you can, like, again, there's multiple ways of solving a question, and so I want you to find the fast way of doing it, right? If you try to work something else out, you may converge on the right answer, but end up wasting a ton of time. So just remind yourself that the fill-in-the-blank, you should be able to find a quick method for doing. Okay, so given that we don't have a rule for this, what we basically need to do is reverse chain rule. We know what happens when we take the derivative of the product of two things. We want to be able to reverse that. So let's remind ourselves what product rule is. So let's see who remembers the fundamental theorem of calculus. If I integrate the derivative of this product, whoops, missing a bracket. What does this evaluate to? Yeah, f times g. Okay, so this is equal to the integral of f prime g plus g prime f dx. So what can we work out from this? Well, I'm going to move one of these to the other side. Which one do we move? We move this one. So I'm going to write the integral of f times g prime d of x is equal to, this is just going to integrate back to f times g. So that just is this, minus the integral of f times g dx. Okay, so we could rearrange the product rule a bit to get this equation, which is integration by parts. But we write it in a little different way. But okay, if I let u equal f of x, that means du is equal to df of x dx. That means v, if I let that equal to g of x, we're going to get dv is equal to g of x dx, which means I can rewrite that thing up there to be this, which is we are going to call and use integration by parts. So this is going to be very important. The integral of u dv is equal to uv minus integral v du. Very, very, very important. I want you to write this down every time you do an integration by parts, just in the corner. I want you to use it so many times that you'll never forget it. Okay, so this may seem like a bunch of nonsense, but let's deploy this on an example. So if I wanted to integrate x cos x, you can see here that there's a product, right? So as soon as you start seeing products, one of the things you may want to consider is using an integration by parts. Although an integration by parts is not always required if you have a product. Sometimes a substitution will suffice. So this is what I want to do. I want to use this. So this is how I always start. I write down u, du, dv, and v. I still do this to this day. Okay, so the general strategy here is you want to pick u from this so that it becomes simpler. And you want to make the other thing the remainder. So one of these products has to be u and the other one has to be the rest. So I'm going to choose u to be x, which means du is dx. Agree? Okay, so I've made this u. That means the rest has to be v. So v is going to be cos x dx. dv is here.
Isn't that v?
No, oh, sorry, dv. Thank you. Okay, so if this is the derivative of v, this is what? The antiderivative of v. So what's the antiderivative? So I'm just going to write it like this. It's going to be the integral of cos x dx, which is what? Sine x. Okay. So then I just use this formula to finish, right? So we're going to have, this is equal to uv. So x sine x minus integral v du. Sine x du is dx, which is going to be x sine x minus plus cos x plus c. You have a very confused face. Let's work through it.
You're just using literally that formula.
We're using literally that formula. Reverse product rule is what this is. Okay, let's just, for the sake of it, look at this and take the derivative just to confirm we did it right. So to confirm, which is a good habit, let's look at x sine x plus cos x plus c. Let's take that derivative. What are we going to get? Well, product rule, so that's 1 times sine x plus x times cos x minus sine x plus 0. The sine x's cancel and you get x cos x. Check. It's a good habit to be into, right? Especially on your midterm. You don't have to get any of your integral questions wrong because you have a great way of confirming that you've actually found the right answer. Right? So, especially if you find yourself lingering on questions. If you take an integral and you find it and you take the derivative and you get back the integrand, you've got it right. Move on. You can forget about it. You are 100% right if the derivative of the thing that you integrate gives you back the integrand. It's a great way to move on. Okay, I'm going to make one lap so you guys can sort of absorb this. Absorb.
Wouldn't du be any c value? So you know how we said u was x? Then du would be c.
What?
Like any number.
U is x, so the derivative of u is the derivative of x.
So we don't write c right away. Like wouldn't
What's
the
c?
derivative of x be any number?
No, no. What do you mean any number? The derivative of x with respect to x is 1. So I think you're getting a little bit confused. The derivative of x is 1. Yeah, it's not any number. Okay, so that's the one that we're going to need, that formula there. I'm going to write it on the other board, really big. So again,
I know.
write it huge. The integral of u dv is equal to uv minus integral v du. There's also the definite version, but that's easy. You just have to go ahead and evaluate these as well. Okay, so this is here for the rest of class for us to stare at. You look at that. What can I give you now? Okay. So notice, what would have happened if we would have chosen wrong?
If we chose cos x.
Okay, so let's do this again, but I'm going to do it in a way which was bad. Right? Because there's two natural things to choose. There's a product of two things, x and cos x. So I said x should be u. We could have done it another way. So again, same example.
Would it be wrong or just more complicated?
The point of integration by parts is to produce an integral that's less complicated. It's pointless to make the integral more complicated. But you're right. If I would have made u equal cos x, that means dv would have had to have been x dx, which means v would be the integral of this, so x squared half. And then du would have been minus sine x dx. And the integral would have become what? uv cos x times x squared half minus integral u dv cos x times x dx. Did I do that right? Integral uv minus integral, oh no, v du. I did it backwards. V x squared du, yeah, plus sine x dx. Okay, like we've made something more complicated now. Right, so yeah, integration by parts will fail if you choose the wrong substitutions. Right, so we generally want to choose u so that this du becomes simpler. And when the du becomes simpler, that should make this integral more simple. And you may have to use integration by parts like 3 or 4 times, right? This may require integration by parts. And I'll show you a bunch of other strategies. So you understand that if you do an integration by parts and it doesn't work, you are to throw away that piece of paper and try a different integration by parts. Try different substitution. Or maybe even try using a substitution beforehand. Right? Every time I teach you a method, like my expectation of you is that you're going to be able to utilize a combination of the methods that I've shown you. Right? It's not just going to be an integration by parts. Now, for this midterm, I struggled with this a bit. It's hard to know what technique to use given an integral. That only comes with practice. I don't think you guys can get in enough practice by Monday. So for this midterm, we are telling you what technique to use for the long answer. I'll say, integrate this by parts. Right? Use a substitution to integrate this. But by the final, we expect you to be able to identify which technique to use. Okay, so for this midterm, practice utilizing the techniques. We'll tell you which one to use. But by the final, you have to have a better handle on it. It is one of the learning objectives for you to know which one. Because in the real world, the integral is not going to say, hey, use substitution and integration by parts. Right? If integrals start talking to you, maybe see a doctor. Okay. So again, it may fail. Fail. Bad. I got to get used to failure. Okay. So a piece of terminology was produced last week that I really liked. And this is the notion of a silent one. I really like that. I really like this term that you invented, the silent one. And what I mean, it's a good term. It's a good term. It's because if you have this, like a number A, the number A is always a product. 1 times A. So it's like a silent one. I really like it. Okay, so don't forget about these silent ones, right? So, given that strong hint, integrate this. I'll make it even stronger. Silent one, not so silent. 1 ln x, integrate 1 ln x. Well, there's only 2 things, so try one and then try the other.
So this wouldn't be on short answer, this would be on long answer, right?
No, there's an integration by parts that's a short answer. Because the first one we did today, that is easy.
But you will also tell us which technique to use for the short answer.
I think so. The short answer ones will be trivial integrals. Right? Some of them have a bunch of techniques that you can use, but the point is they'll be very simple integrals to take. I actually think that may be one of the short answers, something similar to that.
Wait, what about? I don't letting 1 equal the derivative of something.
That's fine.
But I only.
But it wouldn't be 1, right? It'd be 1 dx.
Yeah,
Yeah.
we're just.
The whole integral has to be matched.
Oh, okay.
Some people say take
What?
this minus.
Any derivative of 1. And then the derivative of 1 x ln x, right? I don't know why I'm so sus about this. It's like, I don't know.
Sus.
Yeah.
Why so sus, dude?
I feel sus about this, what I'm saying. Okay. I don't know.
You never get any of these.
What are choosing? Okay, he said it would be 1 dx. That's like, so 1 times the dx is 1 as well.
Yeah.
And then like ln x is something.
Yeah, that's why I got this, so that's 0.
times. Sorry, oh, I was hearing something.
So you just run on X plus Y, and then du equals dx. So it would be just multiply.
You're just too good at it.
What's the integral?
Lazy, just do it.
What's the antiderivative of x on the derivative?
After you finish taking the derivative, see that you get it back.
How you derive from x?
Because the integral of ln x is not 1
No, there's no.
What? What?
not because the answer would have been 1 over x. Because we're just finding the integral of ln x, right? So if we were to take the integral of ln x, the answer of this question would be 1 over x. But it isn't. I mean, like, your answer, like what you're saying to me right now is that this equals 1 over x. Well, then the answer is 1 over x.
Plus C.
Then you're done. You don't need to do anything.
No, I think he's just trying to show you how one, like.
The thing is, like, why would I use this when I know the answer?
That doesn't prove that.
No,
Like, it's like how you can.
that's what I'm saying, is that if we go by your, I'm not saying you are wrong. I'm not trying to be offensive anyway, or whatever, but like, it's just, you don't need to use this at this point. You have to use it to find the answer, so it's clearly not 1 over x. It's something else.
What?
What if we let dv equal dx, and then he would be x.
Oh, yeah.
And then he would be x.
The other way.
I don't think that's ever happened.
Oh, yeah, that makes sense. I can do it the other way.
Yeah, because 1 dx is the derivative of just x, right? Like, that one, and then that makes sense, and then u would be ln x, and this would be 1 over x.
So like we have these now.
Okay, sure. So that's the figure of x ln, or x ln x minus the integral of.
Wait, so dv is dx?
I'm sorry?
dv is dx?
Yeah.
And then what's the?
No, dv is 1, or you said dv?
Yeah.
Sorry, we're using these ones exactly. So,
dv.
yeah, dv is dx.
What's the, like, antiderivative of that?
So it's just, no, so the antiderivative of what? Is just x. Because you're bringing the dx over from the dv side. Because the dv by dx, and you're bringing over the dx. What? Yeah.
So then what's v?
V is x. V is x, dv is dx. U is ln x, so u is 1 over x. Right?
But no, we should put it to that.
And then x dx, which equals ln x minus x squared over 2. Is that the answer?
Oops.
X times 1 over x minus 1.
Is it du?
Yeah, it is du.
Yeah.
Exactly. I need to like write a line through
Yeah.
for something.
The integral of 1 by 1 over x.
The integral.
Okay, wait. I still
What's
don't.
the reverse part?
That doesn't make sense.
Yeah. So
What if we?
that's what you said. Okay, so do it again. Okay, what's going to be now?
Something for the other stuff.
It's going to be 1 over x.
You're gonna have to take the integral of ln x. If you do the integral of ln x, then why didn't you use the
1 over x squared.
It's pretty funny.
2 over x squared.
It used to be full.
So minus 1 over x squared.
There was never a waiting list.
Bro.
not the antiderivative of ln x? We're trying to There's only one other option.
I did, yeah.
You
You didn't even apply.
The thing is, mostly gets on average.
That runs off this year. My mom used like funds to renovate our home. She like took out the RUC education savings fund. Yeah, she used it on our house to renovate.
Nice. Yo.
Yeah, she's like, no, because she's like, OSAR's gonna give you money, it's fine, we don't need this, I'm gonna use it to renovate.
And then my dad's not for dog.
Yeah, and then, yeah, so now, you see it's not even
Wait.
at least you get service somewhere. Oh my god, don't even service on subway. Dude, I'll like walk down the street and then it'll disappear and I'm like, I'm servicing my house. Really?
Just gonna go forever, yeah, it's gonna go forever.
Unless I went outside. Yeah. It's a little bit better. Yeah. There's at least 2 bars.
So guys, I did it. I tried to do it the other
No, I mean, what's the antiderivative?
The antiderivative of 1 over x.
The antiderivative of 1.
That's what we're trying to find out.
Yeah.
Wait.
That's, I explained this to them. I was like, that's what we're trying to find out.
Wait, so it's ln x squared minus 1.
Look,
Ln x.
no, the thing is like, okay.
Where are his notes? Like,
No, if you plug
Okay,
in,
wait, his notes are here.
if you plug in 1 over x for du, you're not integrating with respect to c. So anything that, that's what I'm saying. If it's going to be integral of x times 1 over x, you're not integrating with respect to anything. So you can't integrate. You always have to integrate with respect to something, right?
Wait, what the?
You can't just do integral of 1. It has to be integral of 1 dx. I'm sorry.
Good job.
Oh, but we got the other part, right? We got the x on x.
Good job. Oh, wait, no. So, no. So, if the only reason it could be like that if it was integral 1 dx. Because then the antiderivative of 1 would just be x plus c. But the thing is, we have to find a du that equals dx. So that doesn't make sense. Or du equals 1 over
It
x.
was this, right?
I'm sorry?
Well, mainly because log's not defined in the negative direction.
Yeah, but not like with respect to anything.
But we were right.
That's where you're
We're
going.
not.
I'm confused about this part.
No, yeah, that's right. Y times x.
What's this?
Okay, you guys do it?
This is x times 1 over x.
How did he get the dx?
So here's u, here's du,
Guys, that's not there.
here's dv, and here's v. So tell me what substitute.
No, I literally just got it.
What should I choose for you?
I just got it, guys.
What should I choose for you?
Ln x.
Ln x? So if I choose ln x for you, that means everything else has to be dv. That's 1 dx. Okay? So if u is ln x, what's the derivative of u? And dx, right? Okay, the other way you could think about this, but it's a waste of time, is that like this is du by dx, and then you can clear, right? Anyway, so there's a dx here. So if dv is 1 times dx, what's the integral of this? Huh? X? X. Okay. So this is going to be equal to uv. There's u. There's v. Minus the integral of v du. So here's v. And du is 1 over x dx. Okay, this is just 1. So the integral of 1 is x. So you're going to get ln x minus x plus c. X ln x minus x plus c. All right, let's just take the derivative of this to check. So if we do x ln x minus x plus c, we take the derivative of this, what do you get? You get ln x plus x over 1 over x minus 1. So that's 1 minus 1. So you get ln x, that checks out. It's a powerful technique. Yeah.
I feel like it's kind of pedantic, but you know the constant to check out for me, or it's not a But you know how it's minus the integral?
Yeah.
Would that distribute out to the constant as well? Would it be minus x minus c? Because it would be minus x plus c. Right?
Yeah, I never specified what C was.
Doesn't matter.
Not really.
Because
There are
C could be
some
negative.
people who are more
C could be a negative.
pedantic than me that would care.
Okay.
Right?
All right. I'm glad I asked this, but.
All right, let's do another one. Okay, this is a technique called recursive or circular integration by parts. You're expected to know this technique. Integral ex cos x dx. So what do you notice about ex? What's its derivative? What's its integral? So it's not going to move. No matter where we put it, it's going to stay put. Cos of x is kind of a bastard too, because it's not going to get simple or more complicated. It's going to go from cos to sine to cos. But the fact that it goes from cos to sine to cos is exploitable. And I'll show you a neat little trick about how we can use integration by parts twice and do a little bit of rearranging. Or is it by parts twice? No, integration by parts plus rearranging to get the answer that we want. Okay.
Is that what the recursive is?
Yeah, recursive means you're just applying the same thing onto a smaller piece. Right, so you may need to use integration by parts again to resolve the integral that the integration by parts produces. Right, this is how a lot of those equations in these tables are developed, just by repeated applications of integration by parts, and then some mathematician noticed that there's a pattern or something like that governs them. Okay, so we're going to have to be very careful. Right? You may get confused if you keep using the same labels over and over again. Right? If you're just used to using U for substitutions and a U and V for these integration by parts, you're going to run out of letters. So you're going to have to stay really organized to make sure that you're not like cross-pollinating along your variables of same names. So let's do this again. Here's U, here's du, here's v, here's dv. E's not going to move, right? So I'm just going to put that here, which means that the integral of that is this. Okay, so that means the other one should have been cos of x, which means that if I take the derivative of this, you're going to get minus sine x dx. All right, so I'm just going to move that minus to the other side. Okay, so how then can I rewrite this guy? Why did I put dots? I just want to separate. I'm going to do another integration by parts. And I want to indicate that this is the integration by parts for this. Okay, so it's uv cos of x times e to the x minus the integral of v du. dx du is plus sine x dx. Well, this doesn't seem any simpler than the original problem. And so I guess we're just going to have to use integration by parts again. Okay, so I'm going to do integration by parts again. This line means, like, one of the strategies you can do is just number these. Right? You could say this is u naught, v1, v naught, and v naught. If you number them, that's going to help you keep them organized. Otherwise, I don't care if you number them or not. I usually don't. But I'm very careful to indicate that these substitutions are being performed for some integration by parts here. Right, so I usually say I'm going to do IVP on this, just to indicate that these are for that. Okay, so again, I'm just going to choose EX to be the thing that doesn't move. All right, you want to make sure to choose DV, you want to be able to integrate. Don't put something here that you can't integrate. Then that means U is going to be sine X, and that means du is going to be cos x dx. That means I can rewrite this as, okay, so we have cos e to the x plus Now I'm going to perform integration by parts. uv, whoops, that is not correct. Ex cos x plus uv, so that's ex cos x minus integral v du. V is e to the x, du is cos x dx. Okay, but what have you noticed? What's this? That's the original question. Hold on. This is the original question, but it's also over here. Right? So this is equal to this. Yeah? Yes? Just sort of like, okay. Well, just ignore this. So what I want to do is take this and move it to the other side. And when I do that, what are you going to get? You're going to get twice integral ex cos x d of x is equal to e cos x plus ex cos x. I think I may have done this wrong.
Why is your
Oh, hold on, yeah, I think I've done something wrong. What did I screw up?
like you said uv was ex cos x, but it's ex sin x.
Yeah, I think this one, yeah?
The second one.
Thank you. Sin x. Right. Okay, so that means that this should be a sin x. Thank you for that correction. What do we have here? One more step. Isn't that the answer? I just rearranged, right? Okay, so recursive or circular integration by parts, you end up generating the question as part of the solution. And then you can just move it. It's a handy little trick.
Why was that a 2 originally?
Why is this a 2?
Yeah.
Because there's one of them over here and one of them over here. So if I move it to the other side of the equal, you get twice as many of them.
Oh, okay.
That's why I'm trying to get you to ignore the middle thing here.
Oh, okay.
I'm moving this all the way to the other side of the equation. It's a neat trick, right? But it's a hard one to perform, because you have to notice some sort of secular nature of your question, right? So if you see signs, that's a good candidate, because signs will just flip-flop. And EXs are nice sometimes, because you can't simplify them, but you can always integrate them. So just stare at that. We're almost through, so maybe I'll give you guys some more opportunity to work. Oh, here's a good one for you guys to try. Okay. So you guys need a ton of practice with this. Do the Weeby work. Okay, so I want you to try this definite integral, but just do the integration by parts first and then throw in the bounds later. So do this, integral from 0 to 4, x times 1 over e to the x dx. Give that a go. That eventually works out to 1 minus 5 over e to the 4. Integrate by parts. Got to be very organized, because things like getting the wrong sign will really throw things off. It's telling me that u is x.
What's the derivative?
Unless we go for the y thing.
If you want, you can do it like this instead. So
The rotating on y.
that's u.
Like, yeah, it's easier until you get to it's like this part here.
Otherwise, it's just change. We can take the derivatives and things about specifying what the derivative is. With what axis. Prefer that. I'm gonna do it.
Okay.
I'm trying to save you. You're not clear.
Wait, what did you say? U equals X? Okay, that's what I mean.
Started a derivative.
So you need to go to
It's from 0 to 4 as well.
Trust the notation.
It's
It's trying to tell you what.
Yeah.
dv is equal to 1 over e to the s dx.
Well, 1 over e to the x.
If you're choosing u to be f, yeah.
Just equals. Oh, okay, sure. It's the bottom minus the top, right? It's the bottom. 0 and the top. Oh, yeah, it's from 0 to, right, from 0 to 4, so it's 4 minus.
Wait. These are just not getting this thing
That always.
0.
Can you tell me? Because the x is on, it's e to the minus x. Yeah, that's the right substitution. Yeah, so if u is x, what's the derivative of u?
No, that's a derivative.
Yeah. You mind if I write it? So if I say what's the derivative with respect to x? If u is x, then what is the derivative of u with respect to x? Then you can go ahead and change it.
So we're trying to find
E to the negative x.
the antiderivative of e to the negative x.
Yes.
But you'll do that every time that is clear in this. I just skip it.
It's going to be negative.
You overhead here, you get the d.
No, so the chain rule happens when you get the x. If it's what is the x, you have to find the derivative of that and then put it
So what we're
behind
doing
it.
here, so if we have this
So like
relation.
e to the negative x.
To the negative x, negative e to the negative x.
No, wait, no, negative x, that's right, because it's like a, here, I'll write it down.
Basically, it's telling you exactly what happens. The derivative of these is this.
So now what's the four?
It's the integral.
So it's gonna be
That actually plays out with the notation. You gotta put the, you want to take the integral dv over d.
Here's my explanation.
1 over e to the x dx.
As to why
Yeah, I'm just
you
really doing those exact substitutions, and then it's telling you the population.
bring down that exponent.
Yeah. How you going, ladies?
That's the derivative of e
What was your
to the negative x. Okay, well.
Yeah, you should try to do it like I
E to
do.
the negative x.
The antiderivative of it?
Yeah.
You said the same thing.
Like to this day, if I'm doing a real integration by
No,
myself for
this is not
myself,
the
I still
derivative.
say that.
So the derivative is also negative?
No, the antiderivative of
I don't know
negative e
which
to the
one's
negative
okay
x
for
is
what.
e to the negative x.
Yeah, the derivative of
So these are being multiplied.
Yes, yes,
which is the
Then you should have x squared.
Okay.
which makes sense.
Then what's the it's not like the one that
I understand, yeah, but writing next.
The derivative of negative
It's better just
e
to
to the
organize.
negative
Uh,
x is
So
equal to
we did this once.
e to the negative x.
Okay.
Okay, so that's the
I
derivative.
got close.
Okay, well, write down, don't be, stay organized, so it'll be helpful. Especially when things get all one. You may have to use integration by parts twice, and also a circular one.
squared and then b x. So what's similar to that?
So x squared dx, right? And then this will be x cubed over. Yes.
So did you isolate it? So what product?
No, you're right.
Like what two things are being seen?
I like did it, I did that.
We want to get this guy and then
And then I found
Well,
out
let's
like
see.
this stuff is you only
So
use
you would be this.
0 to 4 and 6.
Ah, well, this is different than that.
Yeah, but I found it also. You only use a better word for this.
Yeah, once you're trying to find the definition.
because the minus ones will cancel out.
1 over 0 minus x.
So we get that.
This equal to the integral of e to the minus x.
Right. negative x, negative change.
So that's my
Well, once you and you have to perform the.
No, this would give me. So I'm not sure.
It's close, but that's.
The negative x
like, this is just
You can do it multiple times.
Negative e to the power x.
yeah, which you bring it down, it becomes negative 1.
What is this?
I think that's
To you. That's to you.
You're gonna have to correct all this time.
Oh, you brought it.
I actually don't understand how to generate.
just,
Plus. Wouldn't this just be e to the x?
the negative x
You're right.
this negative.
Okay, so let's do it again. So, let's copy this first.
Did you guys get close to
No.
Minus.
I got something.
Like, you got, like, just memorize.
Well, it plus.
You need to minus the b again.
That's why I want you to write it down every time.
This thing.
I want you to write down this every time.
We're not going into this right
You do it for the other part too. The UV part.
Yeah.
We're
So you wrote it down.
this to something new, right? This term.
UV from
This term is negative.
Okay, well, you have the negative.
This is the second part.
Yeah.
It's not plus.
That.
Just do it that one. But
Yeah, I got-
I did it that way, but it's still didn't get, I got something close to it.
Or minus
over
e
there.
to the
Ah.
So
negative.
that's what I'm trying to say. So this
Is it
one
negative?
Okay.
Minus?
You got u times
Anyway, I just started my process.
Or negative e.
Starting over.
Negative 1 over.
Or, yeah.
So negative 4 e. This is a power of
Wait,
negative.
Kufa, why negative 4?
Because just like this.
Ah, sure.
Same thing, but
Yeah,
like
that's
you're
the
just
same shit,
saying,
same
yeah,
shit.
it's just negative, because you have a negative.
Minus, minus, so it's the
Negative 4.
Yeah.
Long here.
So wait, what is your V? What does V equal to?
G is negative e to negative x.
Negative E to negative X.
He's like telling us everything. You're telling us everything.
You're telling me.
Look at this.
Okay, plug that shit in.
Then minus.
What's the derivative of that? That's exact.
I did actually
as soon as I got
think
it.
I took somebody else.
Doing one of the steps. Notice, so E is this. Notice that if I integrate E, you're gonna get P. So that means P is equal to E.
That's gonna say it's like this
If
big.
E is this, that means that G is equal to
I mean, yeah, we can.
What?
Oh, no, we can't do that. It's gonna be multiplied. We'll keep going, we'll keep trying.
Yeah.
Let's see if it equals this.
Here you just screwed up. Yeah, it's a common mistake to use long single state slices. You see it like over and a common mistake to
This will equal that.
people forget about the change. You don't only get one over time. So
The problem we don't understand is that it's circular, but it's inside the circle, go back and forth. This x continues to go bigger and bigger.
I was checking this out.
Did we pick the wrong one? We'll pick it up.
don't forget. Oh, so yeah. Yeah, nice. You should write. Just write minus 0 for the mark.
No, so then plus, it was minus that one.
Yeah, I don't understand. I don't understand.
Right? And then if you just try.
It's just the same thing you just used. You're gonna get minus 1 over e to the 4 minus 1 over e to 0.
Do I
I made this page
Oh, you did a substitution?
and then another 4. Yeah, it's not like that. I thought the boundary was plus 1
Well, I'm just saying, you know how to take the integral of 1 over 8. Now you're saying integral of minus 1 over 8. Well, yeah, but like, you're saying the integral of positive version is actually. You could take the negative version and replace it with the negative.
The error of things.
This is sort of something where I give you a hammer and not. That's okay. You don't have to integration by parts. You know what my gun said.
Is that how you read it? Is that how you read it?
You're just going to get like something that looks like something that's correct. You know? If it's not making sense to you, it's not going to make sense to the markers. You know what I mean? So if it doesn't make sense, just stop. And then say, I can't continue because of this. That will get you far. Faking it like this. Well, it's not really faking it. You're just continuing to do this. Don't be afraid to stop. But again, you have it.
Did you guys? Where'd you catch it? I got up to here, and that's not right.
There's no way to tell ahead of time.
So I changed mine, so it's actually right now. So you work great. Thank you.
So generally,
DV
what you want to try
was it negative? Okay, so it chose DV as 1.
See how we use it?
Right.
The idea is that
This is our, this whole thing. This plus that.
different.
Yeah.
So you want to make it so that then you integral it
And you were so
something that
that.
you can do.
Just
Otherwise, there's no point in writing it.
It would be e to the negative x. What derivative do we get? What can we derive in order to get that? So negative e to the negative x. The derivative of that is negative e to the negative x times
Every
negative
week I have to say, I cannot, now, it's not like I'm trying to hold this problem.
So left side.
There really is no way of coming at what x equals to which substitution.
Using
It's just gotta, integrals are hard, so you give them
yeah.
try.
Well, anyways, I did everything you get to that, and I plugged it into here, obviously, and then so then I just simplified it, so now it's yeah, but I still got it wrong. I just multiplied it. It's just easier for me.
All right, I'll work it out. I'll give you another one.
Why is it -4?
Okay, so generally speaking,
Oh yeah, that was the same.
I was just talking about how to make these choices. So I'll give you a
1
good
minus a over d to the
sort of heuristic to use.
whatever that equals.
Okay, so notice that we're trying to rewrite an integral that we can't take into a difference. Right, so we're reducing an integral to a different integral. Right, so the idea is you got to make this simpler than the original question, or there was no point in doing integration by parts, with the exception of this circular reasoning type of thing. So, given that the subsequent integral is going to have a du in it, right? If I make this x, my du, this is as simple as du can get. So that's a good candidate for that. That means this is obligated to be this. So what's the derivative of 1 over e to the x dx? Yeah, minus 1 over e to the x. A lot of you have problems with this. E to the x is the simplest possible thing we can give you to integrate and take the derivative of. So just be mindful of that. I want you to set up your integration by parts exactly how I'm doing it on the board. It will help you. Right? U, du, v, d. Whenever I do these substitutions or integrals or integration by parts, I'm very deliberately like signaling what my substitutions are and trying to stay organized. This is crucial for doing these integrals. You must stay organized. Plus, you'll get more bonus marks. You'll get partial marks if you do it wrong, if you set up things properly. Okay, so this is the substitution that I chose. So let me just take this out. So we're going to get what? And just for the time being, let's forget about the bounds. You're going to get uv. So uv minus 1 over e to the x minus the integral of v. That's minus 1 over e to the x du, which is d to the x. Great. This is way simpler than the original one. So we're going to get minus x over e to the x plus minus 1 over e to the x plus c as the integral. Okay, so I'm going to take this. I'm going to now do the definite integral. So we got to go from 0 to 4 of x over e to the x d of x. That's going to be equal to minus x e to the x plus minus 1 over e to the x from 0 to 4. I know over there I put it on both, but you can just do it like this too. Okay, so it's always top minus bottom. So top minus bottom, 0, write your zeros, plus minus 1 over 1. So this is going to be, what do I get? 1 minus, 5 e to the 4.
Why is it over 1? Why is it negative 1 over 1?
If I put a 0 into here, you're going to get minus 1 over e to the 0.
Yeah.
Yeah.
Oh, it doesn't make a
You
difference.
got that? 1 minus 5?
Yeah,
Can we go something else?
Is that minus 1?
I don't get it. It's 0, it's not negative 1.
What?
It's from 0 to 4, isn't it?
0 to 4. So this is what I get when I plug in 4, and this is what I get when I plug in 0.
Minus 4 minus 1.
But what about...
I'm doing it like across the whole thing. It doesn't matter if you do it individually or across the whole thing. You want me to do it the other way? It will work out the same way.
How did I get them? I don't know.
I don't know. You fail at everything. Okay, let's do more. Let's do more.
Yeah, this, like I'm simply... 1 over e to the 4.
Oh, wait, I think I got
Is there a negative?
we just got 1 instead of negative. Yeah, instead of like adding.
Okay, may have to use integration by parts a bunch of times. So here's an example. Integral x squared e to the x dx. Now remember what I told you? We have to make it so that the new integral that we produce is simpler. E to the x doesn't move. Right? I hate when these things show up because it's really, well, it's nice because we can integrate and differentiate it, but it's not very useful for reducing things. Given that this won't help us reduce anything, we're stuck with this to be u. But if the first one is this, whoops. Okay, what I want you to notice is that the derivative of x squared goes to 2x, goes to 2. So this thing is becoming more simple. You're just going to have to do integration by parts twice. So give that a try. The first so I'm giving you the first substitution. Use this as your first substitution. So I guess dv here is going to have to be ex dx. And v is going to have to be the integral of ex dx, which is super easy. Okay? So this is going to be equal to what? uv minus integral v du. Okay? Oh, maybe I'll do it, and then I'll give you a different one. Okay, so this is the new integral that we produced. It's still not that great. Let me just move the 2 out here. So what can we do? Well, let's do IB integration by parts again. U du. So I'm going to choose u to be x, du to be dx. That's great. It's disappeared. That means dv has to be the integral of ex dx. Whoops. That means dv is ex dx. What remains? Thereby v is going to be the integral of ex dx, which is equal to e to the x, which means this is further. Jesus, Murphy, that's terrible. It's going to be equal to x squared e to the x minus 2 times the integration by parts uv x e to the x minus integral v du. So this v du. All right. So this is actually equal to x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Okay. You guys have to do integration by parts twice. But you should always be striving. This v should always be easier than the integration that you started with. Unless you're trying to set up one of these circular integration by parts. Right? Because we always need to be able to integrate v.
Can we safely say u is always going to be the thing that's not e to the x?
Nope.
Oh.
I'm never able to give you these general rules because there's always going to be an exception where you won't do it. You can say things like, it's a good heuristic, it's a good, you guys know what the word heuristic means? Like a loose guideline for doing something.
So yes.
It's, yes.
Yeah? Okay.
Well, e to the x just never moves, so it can never be involved in the thing that's simplifying something. Right? But again, that's not a general statement.
But on our tests, we don't.
Well, definitely on your test, you shouldn't think like this, right? Before you start an integration by parts, you should stop and say, what is this going to produce? Like, what is my strategy here? Just don't go into it headstrong. Right? Like here, you should realize that after 2 integration by parts, this will disappear. That's what you need to realize. Do a ton of practice. Do all the Weeby work and more. Okay, I'm going to give you some exercises now. And I hope you guys stay and try some of them. Okay, so here's the tricky part, though. You may not need integration by parts. Okay? So don't look at every integral now and use integration by parts. Use it when you need it. Maybe try this one first. Do this one first. Okay, give those a try. Otherwise, have a good day.
Where is this here textbook that you're using?
Doesn't matter. They're the latest